Hello students, the next topic is standard electrode potentials and chemical reactivity. After going through oxidation states, now we are clear and about ionization enthalpies of transition elements. So now we will analyze their standard electrode potential values. Actually, standard electrode potential values are calculated in solution. So as per ionization enthalpy, thermodynamic stability of the compounds of transition elements can be evaluated in terms of magnitude of ionization enthalpies of the metal. And the main point is that smaller the ionization enthalpy of the metal, stabler is its compound. So do remember, if the magnitude of ionization enthalpy is lower, so the compounds formed by that element will be more stable. For example, this is again important. Nickel 2. Nickel 2 means nickel is in +2 oxidation state. So nickel 2 compounds are more stable than platinum 2. They both belong from the same group. Whereas platinum 4 compounds are more stable than nickel 4 compounds. And sometimes the question is asked as per this compound. Yes, this compound is a complex compound and we name it as potassium hexachlorido platinate 2. So this is compound of platinum in +4 oxidation state. So platinum in this case is in +4 oxidation state, whereas no such compound of nickel is found in 4 oxidation state. Okay, so now how can we analyze this? So this table is given and the magnitude of first and second ionization enthalpies of nickel and platinum is given. So first two ionization enthalpies of nickel, that is 2.49 into 10 raised to power 3 kilojoules per mole, and for platinum it's 2.66 into 10 raised to power 3. This shows that platinum has greater magnitude, so its compound in +2 oxidation state will be unstable. Whereas for nickel, the compound will be more stable because magnitude of first two ionization enthalpies is smaller. Now, for the same elements, if we analyze ionization enthalpy 3 and 4, so it has been found that for nickel it's 8.80 into 10 raised to power 3, whereas for platinum it's 6.70 into 10 raised to power 3. So this shows that platinum in +4 oxidation state has lower magnitude of ionization enthalpies, hence its compounds will be more stable. Okay, right? So this gives us the stability of the compounds. In solution, the stability of compounds depends upon electrode potential values rather than ionization enthalpies. And electrode potential values, they depend on 3 factors. First one is sublimation or atomization. Second one is ionization enthalpy, and third one is hydration enthalpy. What is sublimation or atomization? As we know that metals, they exist in solid state, and in order to provide ionization enthalpy, we have to first of all convert them to isolated gaseous atom, that same metal in gaseous state. So when the number of metals or atoms, they are separated into individual atoms, that is called enthalpy of atomization, whatever energy is provided at that moment. This is sublimation enthalpy or enthalpy of atomization. Now the metal has been changed or it has been converted to its gaseous state. That means now we will have isolated gaseous atoms. At that point, the energy which is provided, that is called as ionization enthalpy, and then electron is removed. Again, when electron is removed, this will be called as ionization enthalpy. Up to this, we have generally used these both the terms. Now, the third step involves that this metal in gaseous form, metal ion in gaseous form, it will be dissolved in water to convert it into M positive aqueous, and during this process the amount of energy is released. that released amount of energy is called as hydration enthalpy. Whereas in first two steps, for sublimation we have to provide energy or energy will be absorbed, whereas for removing that electron, again energy is absorbed. But in third step there is release of energy, and this will determine, because in two steps there is involvement of energy and in third step there is release. So the magnitude of the hydration enthalpy, if it is more, so the value of electrode reduction potential comes in negative. If the value of hydration enthalpy is less, then it comes in positive. Okay. In +1 we have discussed the reducing nature of lithium, why lithium is considered to be most powerful reducing agent. Again, that was explained on these three factors. So the electrode potentials are a measure of enthalpy change, thermodynamic stability. Hence, quantitatively, the stability of transition metal ions in different oxidation states can be determined on the basis of electrode potential values. Lower the electrode potential values, more negative the standard reduction potential of the electrode, and more stable is the oxidation state of transition metal in aqueous medium. Very important, you should remember these points. These are very, very important points. Let me draw a star. Okay, is it clear? Just go through this once again. This topic is very important. So final conclusion is that more stable the oxidation state of transition element in its aqueous medium when the reduction potential values are in negative. On the basis of above data, table is given for transition elements which shows standard reduction potential values. Analyze this carefully. There are two values. One is M2 positive to M, and second one is M3 positive to M2 positive. What does it mean? M2 positive means for titanium, if we take example of titanium, titanium has atomic number 22, right? And its electronic configuration can be written as 3d2 and 4s2. 3d2, 4s2. This is 3d subshell and this one is 4s subshell. So two electrons, they will be in 4s. Two electrons will be in 4s, 1, 2, and 2 in d. That's why we have discussed all the ionization enthalpies in detail, so you have to remember that on the basis of that. Now, if we have to remove two electrons, or we say that this titanium is in +2 oxidation state. So how it will be in +2 oxidation state? By the removal of these two electrons. These two electrons are removed. So now the metal is in +2 oxidation state. And we are to change it, that is titanium, can I write it? Titanium 2 positive will be changed to its ground state, titanium, right? So when this transformation takes place, so first of all metal has been changed, and during that process energy is required, and then it is dissolved in water. So the magnitude that comes out to be, that is of these two steps, sublimation enthalpy and ionization enthalpy, and to that of hydration enthalpy, it was found that magnitude of hydration enthalpy is more, hence the value comes out in negative. Okay, same thing has happened, but do remember it is in when the change takes place from +2 to ground state. Likewise, the values are given for other elements except copper. Copper is exception because its value is in positive, whereas rest have negative values. And more negative the standard reduction potentials, so more is the stability of that oxidation state. Now, why copper has this positive value? Copper has this positive value of standard reduction potential, reason being, for copper the reduction potential value is in positive. Reason being, we have to go back to these three factors on the basis of which we can determine reduction potential values. For copper, magnitude of sublimation or enthalpy of sublimation, that is energy required, and ionization enthalpy. So magnitude of these two is greater than that of energy released in third step. Okay, once again, the magnitude of sublimation enthalpy, enthalpy of sublimation, and ionization enthalpy is greater than hydration enthalpy. So hydration enthalpy is in negative, whereas these two are in positive. If the value of if the magnitude of these two is greater, so what will be the resultant? So resultant comes out to be in positive. But if the magnitude of hydration enthalpy is greater, so it comes out in negative. So that's why copper has positive oxidation state, and you might have seen that it does not liberate hydrogen on reaction with most of the acids. In the same manner, the reduction potential values for transition from M3 positive to M2 positive are given in next line. For titanium it's negative, for vanadium it's negative, chromium negative. Now manganese and iron as well as cobalt, their standard reduction potential values are positive. The reason is same, on the basis of magnitude of hydration enthalpy to that of ionization and sublimation enthalpies. In the given tables or graph, the trends in M2 positive to M standard electrode potentials are given for first transition series. Scandium is not given because scandium shows only one oxidation state, that is +3 oxidation state is the more stable oxidation state. So that's why scandium is missing. The data observed and calculated values for the standard reduction potential, so almost it's almost same. Then the table 8.4, again this is thermodynamic data of ionization enthalpies and standard reduction potential value. This is enthalpy of atomization for titanium, this is ionization enthalpy, magnitude of the two, and then hydration enthalpy. So likewise E0 value for particular elements they are given. Okay, now the most important part is trends in M2 positive to M standard electrode potential. Just note these points, these are very important points. There is no regular trend in E0 value of M2 positive to M, right? They are totally changing. This is because their ionization enthalpies, that is first ionization enthalpy and second ionization enthalpies and sublimation enthalpies, they do not show regular trend. The general trend towards the less negative E0 value along the series is due to general increase in sum of first and second ionization enthalpies. So that's why the magnitude generally it goes on decreasing. There are certain exceptions also. Copper shows unique behavior, already discussed. It has positive E0 value, and that's why it cannot liberate hydrogen gas on reaction with acids. It reacts only with oxidizing agents such as HNO3 and H2SO4, which are reduced. Again, why it has positive value? That is due to sum of enthalpies of sublimation and ionization is not balanced by hydration enthalpy. Okay, this we have already discussed. Then the E0 of manganese, nickel and zinc are more negative than expected. So this is for manganese. Yes, you can see manganese. Then nickel 0.2 0.25, and then for zinc minus 0.76. Because of their greater stability in half filled for D5 in manganese, and that is in Mn2 positive, and completely filled D10 subshell in zinc 2 positive. Nickel is due to its high negative enthalpy of hydration for nickel, so it is exceptional behavior for nickel. Okay, you have to note these points. In the same manner, the trends for M3 positive to M2 positive are given. A very low value of scandium 3 positive to scandium 2 positive, not given in the table, reflects the stability. So low value means more stability of that ion in that particular oxidation state. So by releasing 3 electrons, it will acquire noble gas configuration. Then towards the end, the highest value of zinc is on account of very high stability of Zn2 positive, so it will not be converted into Zn3 positive, or Zn3 positive will be easily converted into Zn2 positive. So D10 configuration is there. Then comparatively, high value of E0 shown by Mn2 positive. This is very stable, is on account of, again, if you remember the electronic configuration of these all the ions in +2 oxidation state and +3 oxidation state, I think it will be easier to remember these. So just whenever there is any change in stability factor, just go to their electronic configuration and you will get the idea. Okay, so comparatively low values of Fe3 positive to Fe2 positive, extra stability of Fe3 positive because it will acquire D5 electronic configuration. Then for vanadium, V2 positive ion due to its half-filled T2G3. This is as per that CFT, crystal filled theory. Okay, so these are the trends. To remember these 10 trends. The next one is chemical reactivity versus electrode potential values. How can we determine the reactivity of the transition elements on the basis of their standard reduction potential values? So some of the points are given as per their E0 values. For example, the metals of the first transition series, just exception is copper, are relatively more reactive than the other series elements, right? They are oxidized by H positive ions, right, although the rate is very slow. Then titanium, vanadium are passive towards dilute or non-oxidizing acids at room temperature. Again, this has been already explained that the E0 values, less negative E0 values for M2 positive to M along the series indicates decreasing tendency of their divalent cations. More negative values than expected for manganese, nickel and zinc. This is totally on the basis of their greater stability in that oxidation state. The E0 value for redox couple, that is M3 positive to M2 positive, this indicates that Mn3 positive and cobalt, very important, ions are strongest oxidizing agents. Oxidizing agent means they will help in oxidation, but themselves they will get reduced. So they will acquire that stable electronic configuration, so they act as strong oxidizing agents in aqueous solution. In the same manner, if we relate titanium 2 positive, vanadium 2 positive and chromium 2 positive, they act as strongest reducing agents. Very important, this fourth part. So why they act as strongest reducing agent? Now what are reducing agents? Which themselves undergo oxidation. Okay, so because of their acquirement of or attainment of stable electronic configuration, and can liberate hydrogen from dilute acids. Okay, for example, chromium 2 positive ion plus an acid, H positive ion from acid, so it will be oxidized itself to Cr3 positive and reduction is taking place, hydrogen gas is liberated. So dear students, these were very important points related to their standard reduction potential values, when they act as oxidizing agent, when they act as reducing agents. Hope you will revise it properly. Thank you.